Hello everyone, welcome to our discussion of section 8.5 where we will be talking about power series. Now in section 8.6 we will expand on our discussion of power series in this section. So these are very important, the power series are very important series in this discussion. So a power series is a series of the form that you can see on the screen here. Any series that we can write in this form. It looks like a polynomial, and as we will see in this in a few seconds, the only difference between a power series and a polynomial is the fact that power series are infinite, as you can see, but polynomials are not. So we can rewrite the same power series in this form, in this notation. And if we do write the power series in this notation, then we can call it a power series in x minus a, or a power series centered at a, or a power series about a. So all these three are different names about the same expression, mathematical expression of the power series. So a power series may converge for some values of x and diverge for other values of x. These are some important things to keep in mind as we move forward with power series. So the sum of a power series is a function, just like that, whose domain is the set of all x for which the series converges. Okay, this is a very interesting thing to remember, that the sum of a power series is a function whose domain is the set of all x for which the series converges. Note that and this is what I said earlier, note that the only difference between f, and a polynomial is that f of x has infinitely many terms. So notice that in a power series of this form, when this x is equal to a, all of the terms are 0. That is regardless of the coefficient and the power, right? If x equals a, regardless of these values of c of n and n, all of the terms are 0 for all n. And this is greater than or equal to 1, because for n equals 0, as we mentioned in the previous section, we'll get 0 to 0 power, and in the discussion about series, that is equal to 1. Only in this discussion we consider that to be 1. When we were taking the limits of functions, we considered that to be an indeterminate case, 0 to 0 power, in which case we applied the L'Hopital rule. But in the discussion about series, 0 to 0 power is taken to be equal to 1. Please remember that, and we mentioned that before. So except n equals 0, that is for n values equal to or greater than 1, not for n equals 0, we know that all terms of the series are equal to 0. And the power series always converges when x equals a. So that's a good application of this information. When x equals a, no matter what the power series, it will always converge. The interval of convergence of a power series. So this is just a definition of what this is. What is the interval of convergence of a power series, which is going to come up a lot as we move forward. So this is the interval that consists of all values of x for which the series converges. In other words, the domain of the function that is the series, the power series. Okay, the set of all x for which the series converges. This page 3 is packed with information which we will use in the upcoming examples. So when I post this on Canvas, these lecture notes on Canvas, please make sure that you carefully go through everything again and remember this in order to completely understand the subject in this section. So all of this is part of a single theorem, and we say that for a given power series, there are only 3 possibilities. And these are the 3 possibilities. The series converges only when x equals a, right? And we just discussed in the previous slide that if x equals a, this power series always converges. So that's one of the cases. So the other case is that this series converges for all x. That is, for all x that are real numbers. In other words, the domain of the series would be, the domain of the function, or the convergence would be over the interval -infinity to infinity. And this case 3, often we have this. There are few cases like that, but most often we will have this case 3. I'd say at least 80% of the cases of the power series that we look at fall under this case 3. There is a positive number r, and this is the radius of conversion, such that the series converges if the absolute value of x minus a, the absolute value of that, is less than r, and diverges, the power series diverges if the absolute value of x minus a is greater than that value we call r. And I'm sure you're already wondering, well, how do we get this r? How do we find it? Usually we use the ratio test, which we discussed in the previous section. Sometimes we use the root test, but most often we use the ratio test to find what this r is. The number r is called the radius of convergence, that, of the power series. For case 1, that's the case where the series converges only when x equals a. That's case 1. For case 1, r is equal to 0, and the interval of convergence is a, just one number, a. Okay. For case 2, that's when the series converges for all x. For case 2, r is equal to infinity. And for the same case, interval of convergence is equal to -infinity to infinity. Okay. For case 3, as I said, this is the most common case we will have. For case 3, interval of convergence can be one of the 4 possibilities. So we have to do quite a bit of investigation when we have this case, which is 80% of the cases. So one possibility is that the absolute value of x minus a is less than some constant, or we can write it as that. So it's going to converge, the power series is going to converge over this interval, which is the same thing as that. As a matter of fact, so we know that that is the same thing as that. Okay? And diverge at both endpoints, shown as parentheses. So if you have parentheses on each side, that means that the interval of convergence is only for values that are within that interval, but at the endpoints, the series diverges. So diverge at both endpoints and converge in the interval. That's what this piece is defining, what that is saying. Again, the parentheses are indicating that the series is shown to be divergent at endpoints, but it is convergent within this interval. Case 2, and we said there are 4 possibilities for case 3. So case 3 being when we have this, there is a positive number r such that this series converges if absolute value of x minus a is less than r and diverges if absolute value of x minus a is greater than r. Okay, so I just wanted to mention that again. When that happens, then the interval of convergence, there are 4 possibilities for it. Notice that the r, we will have to calculate, and there's just one way to calculate that, which is that. So we will figure out the r based on this calculation of this absolute value. But it's the interval of convergence that has 4 possibilities. It's this piece that has one of 4 possibilities. Okay? And to investigate that, we will figure out if it's going to, for one of the possibilities is that the interval of convergence is such that the endpoints are divergent. The series at those endpoints is divergent. Or case 2 and 3, the interval of convergence is such that the series diverges at one endpoint and converge at the other. In other words, we can have this case. That's why I combined 2 and 3 together, to the second and the third possibilities, because the series can diverge at this endpoint, but converge at this endpoint, as shown with this bracket. Or it can converge at the left endpoint and diverge at the right endpoint. And then the fourth case is that the series converges at every point within and at the endpoints of the interval. Okay, so this interval, the series will converge at every point within the interval, including at both endpoints. Okay, and those are the 4 possibilities for calculating the interval of convergence. So here's a note: the ratio test, or sometimes the root test, which is sometimes easier to apply than the ratio test, should be used to determine the radius of convergence r in most cases. And you'll see that we do that. The ratio and root tests always fail when x is an endpoint. So when we're investigating whether the series converges or diverges at the endpoints, we cannot use either the ratio test or the root test. We have to use other checks for the endpoints, other convergence tests for the endpoints. Okay, so to determine the radius of convergence, we can use ratio test, the ratio test, or the root test. 90% of the times the ratio test, and then the other 10% the root test. But at the endpoints of that interval that we just discussed, for the interval of convergence, both of those tests fail, so we have to use another one of those convergence tests that we've used so far. We've discussed several of them. We have to use the other ones. Okay. All right, so let's begin to apply these concepts to some examples to see how all of this works. We begin with this example. They want us to find the radius of convergence and interval of convergence of the following series. So we know that for the radius of convergence, we have to use most likely the ratio test, if not the root test. But for the interval of convergence, for the endpoints of it, for the endpoints of the interval of convergence, we have to use other tests. Okay? So first let's apply the ratio test to find the radius of convergence. It would be good if you pause the video at this point, and because we talked about the ratio test and the root test in section 8.4, so you should have a pretty good idea how to proceed from this point forward. And then unpause the video to see if your result agrees with mine. So applying the ratio test, we have this result n plus 1 times x to n plus 1 power divided by third root of n plus 1 multiplied by, since we're dividing by a sub n, which is this, we flip it, right? We're dividing by this, so which means when I put it in multiplication form, we have to flip this. So we will have third root of n and then divided by minus 1 to n power times x to n power. Okay, we can significantly simplify this. And this x to n power and this x to n power, because everything is being multiplied, they cancel out. We just end up with an x in the numerator. And this, because we have absolute value, this minus 1 to n plus 1 power just drops out. So we will have just x times let's see, and this, does this, no, that doesn't cancel, so we still have the third root of n, and then divided by all of that, divided by the third root of n plus 1. Okay. All right, so now, because n, notice that it starts from 1 to infinity, so the only term here within the absolute value for which we have to keep the absolute value is just this x. And this is, the limit applies only to those terms that have n in them. So we can again simplify that, and I will write that here, that the limit as n goes to infinity would be just the x. I'll put that, or absolute value of x, just to bring it out. Actually, I should have put the absolute value of x here in front. It doesn't matter, but I will do that next. And then apply that to the third root of, I will combine these because they're both third roots, so n over n plus 1. Okay. Then, maybe I should have put the equalities in red to distinguish different pieces of this. And then equals again. This time I'm going to put the absolute value of x in front, and then we're going to divide every term here by n. Every term inside the radical we will divide by n. And we will get 1 in the numerator. N divided by n, we get 1 plus 1 over n. And the absolute value in front, of course. So now, if you apply the, notice that just rearranging term here, going from here to here, makes it easier to apply the limit. And if we do that, this will be just third root of 1, which is 1. So we will end up with absolute value of x times 1, which is equal to absolute value of x. Okay, so what we've determined using the ratio test is that this series converges for this value being, of course, because it's absolute value of x, if it's less than 1 by the ratio test, so let me add that here, by the ratio test, this series that we started with converges when the absolute value of x is less than 1. Right? We know that from our discussion in the previous section. So because of that, then the radius of convergence, which is one of the things they've asked us to find, is equal to 1, which is whatever that is, that constant is on the other side. So the radius is r equals 1. We've answered that question. However, notice that in our discussion we said that both the ratio test and the root test always fail when x is an endpoint of the interval of convergence. That means, actually, before that, we know that this is the radius of convergence, which means, since absolute value of x is less than 1, that's when the series converges, then we have x. This is our interval of convergence that we have to investigate at endpoints. So we know that between -1 and 1, the series converges. But we don't know anything about the endpoints yet. And as we mentioned here, the ratio and the root tests always fail when x is an endpoint of the interval of convergence. So the endpoints must be checked with some other test. So we have to use some other test to check the endpoints, to check whether this series converges or diverges at x equals 1 and x equals -1. So let us check for x equals 1. So when x equals 1, and like that, hopefully using different colors will eliminate some of the clutter as I go through this procedure. But once you know how 1 works, all the other examples are the same procedure. You will use either the ratio test or the root test to establish the radius of convergence. Then for the endpoints, you will use some other test. They're all like that. Okay, so in this case, when x equals 1, this is our series, right? When x equals 1, this will reduce to -1 to n power divided by the third root of n. So let's write that down. When x equals 1, our series becomes this one. N equals 1, -1 to n power, right? Because x is just 1. And then divided by third root of n. So this looks like an alternating series because of -1 to n power. So let's consider the alternating series test to test the convergence of that series at x equals 1. Okay, so let me we know that Bn, the positive portion of this series, is simply 1 over third root of n. Remember that test? So 1 over, the Bn's are the positive portions of the series. Like that. And just looking at this, we know that every n plus 1 term is always less than 1 over third root of n term. So thus 1 over third root of n plus 1 is always less than or equal to 1 over third root of n, right? That's clear from this expression of the Bn. As larger values of n lead to smaller values of this fraction. So this is going to be a decreasing series of numbers. Okay, so, and this is true for all n. So condition 1 is satisfied. And of course, we're referring to the condition 1 of the alternating series test. Okay. What was the other condition? Do you remember? We take the limit of this, and if it's equal to 0, condition 2 is satisfied. So also, and I will, maybe I should, yeah, I can go to the, let me go to the next page. So I'll keep that on the screen for now. So also, we proved condition 1. Also, as the limit of Bn, as n goes to infinity, is equal to limit of 1 over third root of n, as n goes to infinity. Of course, if n becomes extremely large or infinitely large, then the third root of that will also be infinitely large, and any constant divided by infinitely large number is equal to 0. Thus, condition 2 of the alternating series tests is satisfied. So what we've established is that the series, the original series, does converge when x equals 1. So at this endpoint, the series converges. Now we need to investigate what happens when x equals -1. And of course, we know that when x is in between those two numbers, the series does converge. So before looking at x equals -1, I'll just want to add that. So we say that therefore by the alternating series test, the series converges at x equals 1. Okay. So now we will look at when x is equal to -1. So when we started with this series, since it's off the screen, I don't mind rewriting it so we know what we're doing here, like that, third root of n. So now when x equals -1, what happens? Let's see. We get -1 to n power. This x is going to be -1 to n power divided by third root of n, right? So -1 to nth power multiplied by each other, we get +1, right? So the end result will be 1 divided by +1 divided by third root of n, right? So do you remember what kind of a series is this? So let me write that here. This is basically 1 over n to 1/3 power, right? If you rewrote the denominator using rational exponents, this would be 1 over n to 1/3 power. So this is, as a matter of fact, let me do that. So there, it's more obvious this way. That is that. And then this is which is a P series, right? Which is a P series with P equals 1/3, which is less than or equal to 1, right? Less than or equal to 1. So for the P series to converge, this P, or the power, should be greater than 1, right? But it is less than or equal to 1. So the series diverges at x equals -1. So let me write that down. Diverges at x equals -1. Remember that this series is just the original series when x equals -1. Okay, that's all. Okay, so to wrap all of this into the interval of convergence, for our series is, of course, it's divergent at -1, but it's convergent at 1, so this is how we would show it. And this would be I, capital I, equals that. This is the interval of convergence. Okay, divergent at x equals -1, convergent anywhere in between these two numbers, and also convergent at the end point equals x equals 1. All right, so let's look at another example. It would be a good thing for you to pause at this point because now you've seen one full example. So please pause, spend 15-20 minutes on a piece of scratch paper figuring out the radius of convergence and the interval of convergence for this series. And then hopefully at the end when you unpause the video, our answers agree. Okay, once again, we start with the ratio test. And so here we have that x to n plus 1 power divided by n plus 1 times 3 to n plus 1 power multiplied by, then flip that, we have n times 3 to the n power divided by x to the n power. And of course this we can simplify. So what do we get? We get x to the n power. With this x to the n power cancel, we will have just 1x in the numerator times this n. And then in the denominator, we have the 3 to the n with this 3 to the n cancel out, but 3 to the first power stays, times, of course, n plus 1. Okay. Again, I mean to, because I don't want this to be too cluttered, so these are just equals. Maybe I should have written them in red ink. Okay. So then we can simplify this a little more. Let's do that. The x can come out because the limit applies only to those terms that have n going to infinity. So absolute value of x can come out, and 3 also can come out. And then we have limit as n goes to infinity of that expression, n over n plus 1. Notice that I removed the absolute value for this because n is always positive anyway. So we don't need the absolute value. Once again, just to be able to apply this limit easier, let us rewrite this in a different form. We're just going to divide every term by n. So we have absolute value of x over 3, limit as n goes to infinity of 1 divided by 1 plus 1 over n. So we just divided every term by n. Okay, so now this whole thing will reduce to 1, right? Because if you apply the limit, this will be 0. 1 over 1 is just 1. So we'll end up with multiplying absolute value of x over 3 by 1, which is absolute value of x over 3. So what have we done? We've used the ratio test to determine the radius of convergence. So the series converges when absolute value of x over 3 is less than 1, right? So this tells us that absolute value of x then should be less than 3, or we have x radius of convergence being from -3 to 3, right? This is just that. So by the way, so we can write at this point we can write that the r, well, maybe I should have written it like that. Radius of convergence is equal to 3. Okay. Now the rest of this, what I'm doing here, has to do with determining the interval of convergence, because we need to investigate the endpoints of this interval. We know that the series converges, our series here converges anywhere between these two numbers. But what happens at the two endpoints, we cannot determine using the ratio test. We will have to apply some other test. So when x equals -3, let's see if we have a convergence or a divergence at the left endpoint. So our series, which we began, was this. Began with, it's this one, x to n power divided by n times 3 to n power, right? We began with that. When x equals -3, what happens here? Let's substitute for x with -3. like that. And if we simplify this expression, we will get -1, right? -1 to the n power over n. Over n. This is what we will get. It looks familiar, doesn't it? Because this is the alternating harmonic series, right? We've seen this before. And we know that the alternating harmonic series do converge. We could, because we've seen this result before, at this point you could put an arrow and say, this is an alternating harmonic series and we know it converges. So that would be the conclusion. But I just want to remind you how we established this using the alternating series test. The proof of the fact that the harmonic series itself diverges was done in section 8.2 in your book. So I won't be doing that here because it would take a significant amount of time to show that again. But your book contains that proof within the text for harmonic series which diverge. But this is an alternating harmonic series which converges. And it's got a short proof, so we can show it quickly. So this is a So I write that first, but here is what we can show very quickly. If Bn is equal to 1 over n, we can easily see that 1 over n plus 1 is less than or equal to 1 over n, which means Bn plus 1 is always less than or equal to Bn. So condition 1 is satisfied. And we know that the limit of Bn as n goes to infinity would be the limit of 1 over n as n goes to infinity. Of course, this is 0, therefore condition 2 is satisfied. So we don't have to show this every time we have a alternating harmonic series or an harmonic series. We can just reference back to the work that we've previously done to say that whether one diverges or the other one converges. Okay, so and the conclusion of this test, which was the alternating series test, is that this being an alternating harmonic series, it converges. So that's what's important. So we know that our series does converge at this endpoint when x equals -3. Now we have to test the other side when x equals 3. So when x equals 3, I'm just going to begin with our series and then substitute for x with 3, right? So then we had x to the n power divided by n times 3 to n power. So that will become 3 to the n power divided by n times 3 to the n power. Of course, this will reduce to, lo and behold, the harmonic series. So at this endpoint, we have harmonic series, and we know that this diverges. It is divergent. Okay, so therefore, we've now evaluated this whole interval. We know that within the interval, the series converges. At x equals -3, it converges. But at x equals 3, as we showed here, it diverges. So let's wrap this up in a final conclusion. Let's see, diverges at x equals 3. Thus, the interval of convergence is -3, 3 parenthesis. Okay. Okay. Let's take a look at another example. Go ahead and pause the video, and then after 15 minutes, once you're finished, unpause the video and see if your answer agrees with this or not. Okay. So I hope you've done that, and now you're back. So taking a look at this, because everything is summed to n power, it's easier, it seems, to apply the root test rather than the ratio test. Okay, so we will do that. N through to of absolute value of n to the n, x to the n, and we have then limit as n goes to infinity. Of course, we can put the n outside of a parenthesis, and then that would cancel with this n, so we end up with I should have put the absolute value of x out here, but it's okay, I'll do it after this. We will have n times x, right? And the powers, the root, the index of this radical expression, and these powers cancel each other out. So we end up with x, or absolute value of x, times limit as n goes to infinity of n. Take a look at this. If you apply the infinity to this, what will happen? Will it converge or diverge? For sure, it'll diverge, right? This is equal to just infinity, because this absolute value of x, whatever that value, times infinity is just infinity. And then, so we have if if x is not equal to 0, right? If x equals to 0 is just, then we will have 0. So the series converges only for x equals 0. So let me write that because this is a very important. So thus, the series converges. If you substitute for x with 0, you won't get infinity, you will get 0. Everywhere else, the series diverges because of this result. The series converges only for x equals 0, and it diverges for all other x. Okay? So when this happens, then the radius of convergence is equal to 0. So let me is that. And when this happens, the interval of convergence is also 0. Right? Just that one value is for which the series converges. So I equals that one value. Like that. And just like that, we are done for this one, with this one. Okay? I hope this is beginning to make sense. It's just the same procedure applied over and over to different examples. Let's go over another example here. It would be a good idea if you pause the video and do some work on a piece of scratch paper at this point. Okay, so this one, let's apply the ratio test again. So limit as n goes to infinity of a n plus 1 over a n equals limit as n goes to infinity of so we have x times, I'm going to simplify this, well, we have that. I will clean this up before because I should have said minus 1 to n plus 1. I will maybe clean this up before posting on Canvas. I should do that. And then times x, 2 times n plus 1, it'll be 2n plus 2 plus 1, it'll be 2n plus 3. Divided by, and the same thing here but factorial. So 2 times n plus 1 would be 2n plus 2 plus 1, 2n plus 3, and then factorial. So 2n plus 3 factorial. All I did was substitute for n with n plus 1, distribute 2 to it, and then add it to 1, and we get that factorial. Then multiplied by, since we're dividing by a sub n, which is that, we have to flip it. So we have 2n plus 1 factorial divided by x2 2n plus 1. Yeah, and then like that. Okay, so then we'll have to simplify this, of course. We have limit as n goes to infinity. This minus 1 to n plus 1, that drops out because it's within the absolute value. So we get, instead we get, what do we get? We get x to the 2n power. With this, x to the 2n power drops out. and then we get x to the 1 power and x to the 3rd power, and so we'll get x to the 3 minus 1, we get x squared here. And then something interesting happens here, right? So let's write this down. Divided by, let's expand this a little bit. So we have 2n plus 3 times 2n plus 2, right? Minus 1 times 2n plus 1 factorial. Now, that x squared, of course, can be put in front. We won't need that, and we don't even need an absolute value for that because x squared will always be positive. But this term and this term cancel out. So we end up with x squared times the limit as n goes to infinity of absolute value of, do we even need the absolute value? No, we don't really need the absolute value, but it's okay. Since I drew it, I don't want to, there's no way for me to erase that now, but maybe later I can do that. So we end up with that. Now, if you apply the limit, this will be 1 over infinity, which will be 0. So we'll have x squared times 0, which is less than 1. So the ratio test leads to a constant that is less than 1. So for sure, our series converges. So for all values of x. Right? Notice that x is been omitted in this result. So all value, no matter what values of x we have, this result is valid. So this is, we already know that the interval of convergence is going to be negative infinity to infinity. So thus, converges for all x, which are real numbers. Values of x, therefore r is equal to infinity, and the interval of convergence like that. So maybe I should repeat the name since we're just introducing this. So this is the radius of convergence, and this is the interval of convergence. I hope this agrees with the work you did on the scratch paper. Okay, so let's see another example. You might want to pause the video and see what solution you will have for this one. Okay, so I will begin again with the familiar ratio test. So we have n plus 1 times x plus 1 to n plus 1 power divided by, of course, 4 to n plus 1 power. Multiply that by, flip this, we have 4 to n power divided by n times x plus 1 to n power inside the absolute value. So this result leads to, we can do quite a bit to simplify this. 4 to the n and 4 to the n go cancel each other out. We end up with a 4 in the denominator. X plus 1 to the n, and that cancel out. We end up with just x plus 1 in the numerator times n plus 1. So we have x plus 1 times n plus 1, and then of course 4 times n. Okay. Now any term that doesn't have n in it can be pulled out of the limit of this absolute value. So we can say x absolute value of x plus 1 divided by 4, and then everything else has n in it, so then times the limit as n goes to infinity of n plus 1 over n. Just to be able to apply the limit easier, we can divide n by n is 1 plus 1 over n. Okay, so let's do that. And then if you apply the limit to this expression, this term will be 0. 1 plus 0 is just 1. So we end up with absolute value of x plus 1 over 4 times 1, which is absolute value of x plus 1 divided by 4. Okay? So now let's explain what we've done. Converges when that quantity is less than 1, right? Less than 1, or absolute value of x plus 1 less than 4. Okay, so therefore the radius, notice that this x, we haven't seen any examples such that this x has a coefficient. If we do, we have to factor that out. I believe we have an example coming up like that, but not so far. So far, every example we've done, we've had either absolute value of x less than something, or in this case, absolute value of x plus 1, where the x has coefficient 1 less than that. So we don't have to factor this expression, and we can just say the radius of conversion is 4. But if x has any coefficient other than 1, let's say 2 or 3 or 5, we'll have to factor that number out. Okay, so that, just keep that in mind until we see an example like that. So from this result, then we know that the radius of conversion is 4. So now this interval, let's see what this interval is. Let's expand this and get rid of the absolute value. we still have to investigate convergence at the endpoints, right? At the endpoints of, so this is going back to basic algebra. Let's solve for x in that. Subtract 1 from all sides, and we get minus 5 here, we get x there, and then 3 there. So we'll have to, we know between negative 5 and 3, our series does converge. But what happens at negative 5 and what happens at 3, we need to investigate that. And then I'll say just thus, and then we'll see the rest of the solution. Let me use another paper here. Okay, so when x equals negative 5, so this is what the series looked like when we started this problem. When we take x to be negative 5, it'll be equal to this. And then this will be, so we'll end up with, we'll have n here. Let's separate this n from the rest of this, so we can then say negative 4 over 4 to n power, and this is equal to minus 1 to n power times n, right? For sure, this is going to diverge, because this, if you, so when we take the limit of this, so let me write that here. Equals infinity, and it's not equal to 0, and we know that we learned something, divergence test, right? So it diverges by the divergence test. So thus that series by the divergence test. Okay. So what happens when x equals 3, the other endpoint? Let's take a look at that. So our original series was this. And then we substitute for x with 3, we get 4 to the n, right? So n over 4 to the n times 4 to the n. And then therefore, so this and this cancel each other out, right? These two. So this and this cancel each other out. We get this series. That. Again, we can apply the divergence test here, and it diverges. The series diverges. So then, because once again, I will use the same line of reasoning here, because limit as n goes to infinity of n equals infinity, and once again, not equal to 0. Diverges by the divergence test. Okay. Okay, so we have a series that diverges at the endpoints, at both endpoints, -5 and 3. So the original series just is convergent from -5 to 3, excluding the endpoints. So let's write that up. And radius of convergence was 4, right? So thus, for this series, is notice that the parentheses at both endpoints indicate divergence at endpoints. Okay, like that. Let's look at another example. It would be a good idea if you paused at this point and see how far you can take this. I'm hoping that your solutions are consistently agreeing with my solutions, and that would be great. Okay. We will do more examples in class. Okay, so I will begin with the ratio test again. So we have 2x minus 1 to n plus 1 power divided by 5 to n plus 1 power times square root of n plus 1 times, let's flip that, so 5 to the n power times square root of n divided by 2x minus 1 to n power inside the absolute value. Okay, so as usual, let's start simplifying this expression. We have limit as n goes to infinity. So 2x minus 1 to n power will cancel with this. We'll just have just 1 2x minus 1. 2x, right, just 1 with power 1 there. Square root of n, there's nothing to cancel that with anything, so we'll keep that. 5 to the n, with 5 to the n cancel out, we'll just have 1 5 left in the denominator. And of course, times the square root of n plus 1. Like that. Anything that doesn't have n in it can be brought outside of the limit of the absolute values. So we can write 2x minus, or absolute value of 2x minus 1 divided by 5, and then times the limit as n goes to infinity. Everything with n in it, of course, is going to be positive. We don't really need the absolute value anymore, and because they're both a square root, so I'm just going to combine them as a square root of n over n plus 1. By now we know how to handle this so that it's easier to apply the limit, so let's do that. And we have absolute value of 2x minus 1 divided by 5, and then limit as n goes to infinity of square root of n over, let's divide everything by n. We get 1 divided by 1 plus 1 over n. Okay. And then, so just apply the limit. We get 1 as a result. So we have 2x minus 1. 1 times all of this, we get that. And so, okay, so what we've determined is that depending on what x value is, if that quantity is less than 1, our series is going to converge by the ratio test. So let's write that down. Converges when that whole thing is less than 1. Of course, if we simplify this or manipulate it algebraically, we will get 2x minus 1 less than 5. So this is what I was saying in the previous example. For this to conclude that 5 is a radius of convergence, the coefficient of x must be positive 1. But it's not in this case. So we cannot conclude that this 5 is the radius of convergence. We have to factor out the inside of the absolute value and make that coefficient equal to 1. Okay, so factoring, so let me write that. Of the form x minus a less than r. Remember, that's how the expression should look like. It's not. So we need that to be positive 1. Okay, so it's just an easy algebraic manipulation to factor that out. So we have two times x minus 1/2, right? Minus 1/2 less than 5. Now we have an x that has a positive 1 coefficient. And of course we have to then divide both sides by 2. So we have absolute value of x minus 1/2 is less than 5/2. So now, since we have this expression that looks like that, we can conclude that the radius of convergence is 5/2. Maybe I can keep that on the screen like this. Okay. Like that. But still we have to investigate the interval of convergence. So or to investigate convergence at endpoints, right? So we have, well, let me start from scratch. So we had, from this, since it's off the screen. So we start with this. Now we have x, again, this is basic algebra that we're doing now. Like that. Okay, so minus 4/2 and 6/2. Okay, after adding positive 1/2 to all sides. So we know that x is going to, or the series is going to converge from -2 to 3. But what happens at -2 and what happens at 3? Let's find out. So when x equals 3, our series reduces to 6 minus 1, 5 to the n power, right? So 5 to the n power. Well, let me not forget to put my notation here. 5 to the n over 5 to the n times square root of n. Okay. And that, so things simplify here. That'll be just 1 over a square root of n. So this is a p series, right? Let me rewrite it like this. So with rational exponents, so this is 1 over n to 1/2 power. This is a p series with a p or power that is less than 1. less than or equal to 1. So it's going to be a divergent p-series. Okay, so this series is divergent because it is a p-series with p equals 1/2, which is less than or equal to 1. Okay, so it's divergent. So we know that our series diverges at this endpoint. So what about when x equals -2? So when x equals -2, this series reduces to this. 2 times -2 is -4, -1 is -5 to n power divided by 5 to the n square root of n, and this reduces to, or simplifies to, -1, right? -1 to consider this, so it'll be -1 to the n power divided by square root of n. So this, let's see, so this again, by alternating series test, we can show that this series converges. So Bn would be the positive portion of this, so 1 over square root of n. Then we can say that this is a decreasing series for the positive values of the series. So we can say 1 over, we can say that Bn, Bn plus 1, I will clean this up before posting on Canvas, is less than or equal to Bn for all n. So this is for all n, and then the limit of that, the limit of Bn as n goes to infinity is limit as n goes to infinity 1 over square root of n, which is of course equal to 0. So this series converges. Converges, and so the interval of convergence then would exclude 3 but include -2. So that. Okay, so including -2 and excluding 3, because the series diverges at 3, x equals 3. Okay, let's take a look at another example. So go ahead, pause the video and see if your solution later agrees with this work that I'm going to do. A big hint is that you would want to start with the ratio test again. Okay? All right. That divided by 1 times 3 times 5 times all those numbers in between times, so this is 2n, so this is still going to be part of the series, but it's going to be before 2n plus 1. So we have 2n minus 1, then we're going to have 2n plus 2 times n plus 1, which would be 2n plus 2 minus 1, which would simplify. Well, let me write it out. So times, instead of n, we have 2 times n plus 1 minus 1, and then we're going to simplify this, times, flip this, since we're dividing, a sub n is all of this. Since we're dividing, let's flip it because we're switching to multiplication. So we have 1 times, 3 times, 5 times, all of those, times, I'm trying to barely fit this here like that. It barely fit. Divided by, it's easier to write denominator, so n plus 1. And of course, there is an absolute value here. So this absolute value on this side closes here, like that. Okay, I was barely able to fit that there. Okay, so things will simplify, right? All of this and all of that simplify. And x to the n and this x to the n simplify, we'll end up with an x. X in the, let's see, so that should be just xn, sorry. So let me get rid of that. I promise I will clean this up before posting on Canvas. So this should be just x to the n power because we're flipping this. Sorry about that error there. So that's that. X to the n and x to the n cancel out. We'll end up with just x in the numerator. So and then we have to simplify this, which will be 2n plus 2 minus 1 or 2n plus 1. X over 2n plus 1. Okay. So x has nothing to do with n. We can pull out absolute value of x and like that. And then limit times the limit as n goes to infinity of 1 over 2n plus 1. Of course, if you apply the limit to this expression, this will be 0. So we will have absolute value of x times 0, which will be 0, and that'll be less than 1. And the direct result of this, of course, because this result is, notice, is independent of x, right? The previous ones, let me, if I can find see this result in the previous example and a bunch of other ones that we did before, that result depended on x. So we had to find the determine the convergence of the endpoints as well as the interval that was already established with this. So, but here there's no x involved. So the result, the series is convergent independent of x. Or we can say that it's convergent for all values of x. Therefore, the radius of convergence is r. Okay, so thus r is equal to infinity for all values in the series. So all values of n in the series, we have the radius of convergence as infinity, and therefore the I should have said that by let me make that statement here. The series let me start from here, because I included this statement for all the other ones. So by the ratio test, the series converges for all real values of x. And the interval of convergence, of course, is negative infinity to infinity. Okay, so I hope this video session was worth your time. I hope you benefited from it. I'll trust that you will let me know if you have any questions. And for now, have a nice day, and I'll see you again next time.